Good morning. So, in the last lecture, I introduced a notion of ADS-CFT correspondence. So, today, I'd like to develop this. So, so I only have 2 more lectures, so I'll summarize some relevant aspects of ADS-CFT correspondence. So, the statement is that suppose we have quantum theory of gravity. In ADS p plus 1 times some compact space. And so this theory can be defined as a limit of string theory, for example, but it can be some other theory of consistent quantum theory of gravity. And so in ADS part, we have this metric. Which is characterized by some quantity of the unit of length, and then there is this metric where z takes value in real number and x is p-dimensional, or in Minkowski signature, it's 1, p minus 1 coordinate. Okay, and yeah, so maybe I should use d. Excuse me. So this is therefore. So yeah, to be consistent with the later notation, I should write this as x mu, where mu goes from 0, 1 to d minus 1. Okay, so this is a d plus 1 dimensional space. And as you can see, the metric is invariant under rescaling of z by some factor and scaling x in the same way. So this part is dimensionless, so we need to provide some quantity of length scale. And this determines the curvature radius of ADS. So for example, if we calculate the Riemann curvature of ADS, it's inversely proportional to the square of this quantity. Okay? And the statement of the ADS-CFT correspondence is that such quantum gravity theory is equivalent as a quantum theory to do the d-dimensional conformalities. And so this arrow means that this is equivalent as a quantum theory. So that means that it's equivalent correspondence of the Hilbert space the Hamiltonian spectrum and operator algebra. So there must be some isomorphism between these. Very often, everything is not completely defined. For example, conformality theory, in principle, one can have a definition of the theory. But for example, if you consider string theory in ADS times some compact space, for example, last time we discussed the example of type 2b string theory on ADS5 plus 5-dimensional sphere, S5. So in that case, the string theory is only defined perturbatively in a coupling constant expansion. But fortunately, in that case, the dual theory is n equal false binomial theory. This is one of the nicest, well understood conformality theory, 4-dimension. So this part, in that case, this part is well defined. This part is only partially defined, partially in the sense of expansion. In that case, in terms of coupling constant. And so in that case, you can think of this as sort of providing necessary definition of this theory. Okay. It's also important to know that there are exceptions to this correspondence. There are cases, especially in lower dimensions, where this correspondence does not hold. So for example, if you consider string theory itself, but instead of think of this as a quantum theory in target space, you just consider string theory worksheet. It's a two-dimensional theory, and it has diffeomorphism because you integrate over modular space. So you can think of this as a quantum gravity theory, although it's a sort of relatively simple type. For such theory, this does not hold. So there is no conformal field theory dual, typically, of two-dimensional worksheet theory. Okay? So there are some, typically what happens is that if the gravitational theory has black hole, we believe that there are corresponding CFT. But it's important to probably understand what class of quantum gravity theory do indeed have CFT dual. So CFT-C means conformal. So that means that this theory has conformal symmetry. So for example, you can rescale coordinate by some overall factor, and then there is a set of operators which scales like some appropriate power, and this delta is called scaling dimension. Okay. So there is a correspondence between Hilbert space, Hamiltonian spectra, etc. And so it's useful to identify this, make some kind of table of correspondence. And for that purpose, it's useful to remind ourselves. So this is a reminder. So this is something we discussed in the last quarter, which is the state operator correspondence of conformal field. So what I'm going to say in the next 5 minutes or so is not about correspondence. So the terminology is a little bit confusing, but this is property of conformal field theory itself. So it's called state operator correspondence. This is not about ADS shift correspondence. This is a property of CFT. And the correspondence in this case is a foreign statement that if you have a local operator O as a function of position of scaling dimension delta, then there is a corresponding state in the Hilbert space. Defined on the time direction times d minus 1 dimensional sphere. So we are considering d-dimensional conformal field theory, but we can consider space like Cauchy surface to be sphere. And then have the time direction, and then evaluate the Hamiltonian with the Hamiltonian eigenvalue delta. Okay, in fact, if this is a primary field, then corresponding state should be in the highest weight state of the highest weight state of the conformal symmetry, with the highest weight being delta. Okay? So the correspondence goes as follows: that if you have a local operator located at x, some position x, then you can consider radial coordinate around that point. And so you can go to the radial direction, and then by definition, if you rescale in the radial direction, the operator is rescaled by delta. Then what you can do is do the conformal transformation. This is a Fourier transformation to map this space to some other space in such a way that metric remains invariant, metric in d dimension remains invariant up to rescaling. And so I think I discussed that in the last quarter, but by conformal rescaling, conformal transformation, you can map this into a cylinder where this is SD minus 1, and then you have a time direction. In this case, Euclidean time. And so you have a Hamiltonian. And so if you have a state O, if you have operator O, then there is a corresponding state for which the eigenvalue of Hamiltonian is delta. Okay, and so if you have this Hilbert space, of CFT on D minus 1 sphere, you can decompose it into irreducible representation. Of conformal algebra. Okay, so whenever you have a symmetry in quantum system, it's often useful to decompose the Hilbert space into representation of that symmetry. And in this case, for it, there's the highest weight. The highest weight representation. You just consider, so well, if the CFT is unitary, then we only consider unitary representation. And the highest weight is delta, and the correspondence is at the primary field. O correspond to highest weight state. Okay, so this is the state of related correspondence. This is, as I said, just a property of conformal fields, although it has a word, correspondence, to it. So now we would like to see how what this implies to ADS side. So let's consider ADS. So again, there are a variety of coordinates we can consider in ADS. But first, let's consider what's called global coordinate. So global coordinate covers maximally extended uncertain space. So uncertain space is a unique, locally unique, homogeneous and isotropic solution to Einstein equation with negative cosmological constant. And one way to visualize it is to be the inside of the cylinder, with boundary being real line times D minus 1 sphere. Okay? And the global coordinate consists of rho, which goes from 0 to infinity, and t. So in Euclidean signature, this is the Lorentzian signature, this is time. And d minus 1, omega d minus 1, which parameterizes sd minus 1. So this is time. And this is a radial coordinate. So you can think of this t and omega as parameterizing the boundary sphere and time direction, and the rho is a direction towards the boundary. Okay? You can think of this t and omega as the same coordinates as t and omega for the sphere, except that we are adding the radial direction to it. So one more dimension. So rho is a new coordinate for the ADS direction, and the metric is given by so this is the same ADS curvature radius, and then cosine hyperbolic square rho dt square plus d rho square plus sine hyperbolic rho square d omega dx. Okay, so this is a metric. As you can see, near the origin, near rho equals 0, this looks like the radial coordinate for the flat direction. And as rho goes to 0, then the time direction goes in the with unit 1. But as rho goes to infinity, as you approach the boundary, this factor grows exponentially. And this is the same thing that as a redshift effect that we discussed towards the end of last lecture. So if you look at the last lecture, you will see that. So now you can ask, suppose, for example, so you have a gravitational theory in isolated space, and in string theory, we can only consider the weak coupling expansion, at least the definition of type 2b in a perturbative description is like that. So it's useful first to consider the situation where you have a bunch of free field in isolated space. So suppose what happens if your bulk theory is almost non-interacting, so it's populated by free fields, the free boson, free scalar field, free fermions, free gauge field, almost free gravitons propagating, and then occasional interaction between them. So in that case, it's useful to understand the non-interacting wave equation in isolated space. So let's first discuss that. So suppose you have a wave equation. So suppose you have, say, for example, Klein-Gordon equation. So that would be box plus m squared phi of rho t of omega. So suppose you try to solve this equation. So there are various things you can do. So for example, if you look at this, then you see that well, this metric is globally hyperbolic. That means that there is actually everywhere a time-like Killing vector. So in that case, it's useful to sort of diagonalize the eigenvalue for the. In that case, it's useful to consider solution which is invariant under time evolution. So, therefore, we can consider the normalizable standing wave of this type of behavior. Okay, and you can see that if you plug this, so then you can have some another function which depends on the rho and omega. And then next thing you can do is to expand this in the spherical harmonics in omega, because there is a rotation symmetry also. So then eventually it will just reduce to one-dimensional, this will reduce to one-dimensional ordinary differential equation. And in fact, it's a very nice kind of differential equation. It's an ordinary differential equation with regular singularity. And you can actually solve this equation using hypergeometric functions. So there is actually exact solution known for this wave equation. And from that, you can actually show that omega is actually equal to delta of plus and minus, plus some integer, where integer is non-negative. So that means that, in fact, this type of mode makes irreducible highest rate representation of conformal symmetry. Because there is a correspondence between state in isolated space and state in conformal field theory. You'd expect that in the free field approximation, the Hilbert space of the free field should be part of the Hilbert space of the conformal field theory by the correspondence. So then you'd expect that the solution to this free wave equation should exhibit representation of conformal symmetry, and indeed it does. That the omega can be identified by the state operator correspondence with the spectrum of operators, and there is a highest weight representation. So delta plus minus should correspond to highest weight. And then if you apply conformal symmetry operator on the boundary or isometry in the bulk, you generate other states. Okay, and then by plugging this into the equation motion, you can find the relation between delta and the mass. And the relation goes like that. Or you can inversely solve this for m. So you can draw some kind of a quadratic equation where m squared is given by minus d over 2 square plus delta minus d over 2 square. So that means that there is this curve, this relation between delta and m has a minimum at d over 2, and there the value is minus d squared over 4. Oh, I'm sorry. So here I'm using the limit unit where ADS radius is 1. So if you restore this, you have to write it in this way. So I should probably write it as ADS 2 square L ADS square. So m square is equal to 1 over L ADS square minus d over 2 square plus delta minus d over 2 square. Okay, so the graph goes, so its intersect is d, so it goes like that. Okay, so there are a few observations I would like to make about this relation. So first of all, this shows that mass square can have slight negative value. So namely that in order for the propagation of this scalar field of mass m to be consistent and make unitary representation in the corresponding conformal algebra, then the mass square should be greater than or equal to minus d minus d squared over 4 L ADS squared. Okay, so this is a famous Brighton-Roland-Friedman bar. So in flat Minkowski space, of course, the lower bound of mass square is 0. That when mass square is equal to 0, the corresponding particle propagates at the speed of light. And then causality and other consideration does not allow particle with mass square to be negative. If you consider particle with mass square being negative, there are a variety of pathology. So for example, naively it looks as though such particle would propagate faster than speed of light. So that violates causality. And if you try to quantize it and find representation, you find that the representation is non-unitary. So either energy can become negative or the Hilbert space inner product become non-indefinite. The corresponding bound in ADS is not 0, but is slightly negative like that. And what Brighton-Roland and Friedman showed was that as far as mass square is greater than or equal to this value, then you can choose appropriate boundary condition in ADS in such a way that corresponding particle is consistent. That it gives you unitary representation, it doesn't violate unitarity, and its Hilbert space has positive definite inner product. Okay, so we can consider such particles. Okay, And so then we can make the dictionary in ADS, CFT. In the case when the gravitation in ADS has this kind of perturbative, almost free field approximation, which is that the one particle state of some field phi with mass m correspond to primary operator O in CFT with conformal dimension delta. And the relation between delta and m is given by this formula. One thing you might notice is that correspondence between delta and m is actually ambiguous when mass is in this range. So this is a range when mass square can become negative, and because we are in this range. So if, as far as mass square is positive, then for each given value of mass, there is a unique delta. But when mass is negative, for example, at this value of mass, it is still allowed by Brighton-Friedman band, but there are actually two kinds of delta associated. And this can be resolved by a choice of boundary condition. What one sees in this case is that if you consider a quantization of particle with mass m squared in this range, then in fact there are two kinds of boundary conditions you can impose. Essentially something like Dirichlet condition and Neumann condition. And corresponding to that choice, there are actually different correspondence between mass and delta. Okay, so there is a little bit of support in that. Okay, so this was the description of the correspondence in the global coordinates of ADS. But for later purpose, it's also useful to discuss Poincare, or what's called Poincare coordinate. Okay, so in the Poincare coordinate, in contrast to the global coordinate that I discussed over there, the metric takes a form of dz squared. Again, I should probably restore ADS scale, so I should write it as LADS squared dz squared plus dx squared z squared, where z, as I said before, goes from 0 to infinity, and x mu is a d minus 1 d-dimensional coordinate. And this is the one that that you land when you take the near horizon limit of, say, D3 plane. Okay, and so in this coordinate, for example, you can ask the boundary condition. So the boundary of ADS is at z goes to infinity. So you can ask what kind of boundary condition you can have. So if you write the solution to wave equation like that, and if you solve the wave equation, you can see that roughly the behavior of the solution to wave equation takes the following form as z goes to infinity. For some function a and b, as z goes to 0. Z goes to 0, as z goes to 0. And we cannot choose a and b to be arbitrary. So by solving wave equation, you can show that if you fix a, b is determined, and if you fix B, A is determined. So you can think of either A or B to be specifying the boundary condition. So when delta is greater than D, then A is determined. A determines the boundary condition. And B is determined by A. So you fix A and then B is determined. So that's sort of the correspondence between A and B. Okay? In CFT side, what this is doing is the following. So suppose you have original CFT Lagrangian, and suppose you add a source to the Lagrangian by the corresponding operators. So suppose there is an operator in CFT corresponding to this, then we may consider deforming this CFT Lagrangian by adding some source. And then for the source, we introduce some kind of source function, A of x, and that A of x corresponds to this A of x. And if you introduce a source, then in fact this develops in general vacuum expectation value of the corresponding operator in the presence of the source, and that is B. So this is like a linear response program. So you introduce a source, and B appears as its response. Okay. So that is the situation when delta is greater than D. But you can see that, and the reason that this happens is that typically when delta is greater than D, then this is smaller than this. So that is how it happens. However, there is an ambiguity where delta is exactly in this range. Because in this range, there is an exchange, in this range there is an exchange symmetry between these two things. So there is actually ambiguity in which one to be regarded as source and which one to be regarded as expectation value. And in fact, depending on the choice of boundary condition, both description is realizable. And so that's corresponding to this twofold ambiguity you have over here. Okay? The same thing applies to energy momentum. So far I have considered the scalar field, but you can also we can also see similar thing happening for the metric and the graviton. So if you have, so in the bulk you have a gravitational theory. So in the weak field approximation, you have Einstein equation. And in the limit when the fluctuation is small, you can approximate Einstein equation as a linear equation for the fluctuation. So you can solve this perturbatively. So for graviton, for such graviton, we can again expand the metric and z squared, dz squared plus dx squared. So that's the original ADS metric. Maybe I should write it in the similar way as I did before. So L ADS squared, z squared, dz squared plus dx squared plus some perturbation. these are like fluctuations, and then expand it like that. So this is like generic parameterization of metric towards the boundary of ADS. So this particular parameterization is called Pfefferman Graham form. And in this case, you can actually relate gamma mu nu of x as an expectation value of energy momentum tensor in conformal pieces. Okay. So you see that there is rather detailed correspondence map between gravity in ADS and the boundary conformal pieces. And so this is sort of beginning of the construction of dictionary between ADS and CFT. Now, here I'd like to tell you a little bit of puzzle about this corresponding table, and the resolution to this puzzle led to some deeper understanding of the mechanism of how ADS-CFT correspondence works. So let me try to tell you that. So as I said, the ADS-CFT correspondence states that if you have CFT, then you have a Hilbert space and you have operator algebra. So on the other hand, in ADS, we have gravity theory inside of this same cylindrical region, where you add this radial coordinate rho to it. And the correspondence means that everything that is happening in ADS, you can have some fluctuation, you can have propagation of particle fluctuation, you can create a black hole, etc., has corresponding description in CFT. So for example, every state here corresponds to every state here, etc. So that means that, for example, if you, especially in this weak field approximation, the perturbative description of gravitational theories that we are considering here, then the bulk phenomena can be described by some local fluctuation of quantum field in the bulk. And then there is a corresponding description over here. So this suggests that if there is some kind of local excitation here, so for example, you can, suppose you excite some scalar field phi to have some value in the bulk, then there must be some corresponding operation, some operation which is like action of some operator on the Hilbert space. So you have a Hilbert space, and then there must be some action of operator on the boundary theory. So it's useful. Of course, I should caution that this is a little bit defining this local excitation in Einstein space requires some care, because here we are talking about gravitational theory. So the notion of local coordinate is not well defined. So how do you specify the position in gravitational theory is a tricky thing, because in order to if you specify position by coordinate, that specification is not invariant under diffeomorphism. So, but there is a way to actually specify local excitation in such a situation in a process called gravitational dressing. So one useful way of doing it is the following. So suppose you are in the boundary of conformal field theory, and suppose you specify a point. Suppose you want to say that there is some excitation happening over here. So how do you specify this in a way that is invariant under diffeomorphism? There is a way of doing it, which is, say, for example, there are many ways of doing it, but one way is to say to do the following. So suppose you fix some point, and suppose you shine the light towards ADS. And then you shine it in such a way that it hits this point. Okay? So then you know the angle and the direction of the light ray. You also specify the affine time along the light ray so that it lands over here. If you do that, then the information of this point can be specified by the diffeomorphic invariant quantity on the boundary. So there is actually, if you have a boundary, then there is actually a way of specifying the position in ADS in this way. So this is a boundary, and this is bulk. And this is called gravitational dressing. Okay, this notion is very similar to the idea of Wilson loop that I discussed in a couple of lectures ago. So there was a similar program when we have gauge symmetry in the bulk. So suppose you have local gauge symmetry in the bulk, like Yang-Mills theory, and well, even Maxwell theory. So suppose you have a Maxwell theory, and suppose you have a Maxwell theory. Suppose you have Maxwell theory. In the bulk. And then suppose you want to specify some electron, some local excitation of electron. How do you do that? Just single electron in the bulk. This again is tricky. This is less philosophically tricky than this one, but mathematically it's very similar. The reason that this is tricky is that this electron operator is not gauge invariant. Under gauge transformation, it transforms like that. So that means that this operator psi is not gauge invariant operator. So suppose you have the vacuum state, which is a physical state. If you add psi on it, it's not more it's not a physical state anymore. So psi does not create a physical state from vacuum. That's a problem in gauge symmetry. So how do you define local excitation of a charged operator in the bulk when the operator is charged with respect to gauge symmetry? Okay, so there's a puzzle. There is actually a way of doing it if you have a boundary. Because if you have a boundary, what you can do is to draw a curve towards the boundary. And then consider first order the exponential of e to the e, where e is the electric charge, times the position, exponential integral of e to the gauge field integral, integrated along this path. And multiply that to psi. Well, maybe I should do it in the opposite direction. So then you start with this operator and then you integrate this A towards the boundary. This is a Wilson line operator. And one of the things about this Wilson line operator is that under gauge transformation, it transforms like that. Okay? So this phase factor cancels this phase factor. You still have this phase factor, but this is fine because you can. This may be the location where you observe it, and you can observe other electrons. So, for example, all other operators at the same point. So under gauge transformation, you get all the same phases. And moreover, as I have told you earlier, that if the boundary is at infinity, then for normalizable gauge transformation, this theta at infinity is frozen. So in fact, this theta y is equal to 0 when the boundary is located at infinity. So therefore, this combination of first order exponential of the gauge field multiplied by this electron operator is gauge invariant. And then this is called So by multiplying Wilson line operator, you can turn the local operator, which is not gauge invariant, and so therefore cannot describe physical excitation of operator of electron, to the gauge invariant operator, which actually describes the physical excitation of the electron. So this is actually the correct operator to describe local excitation of the electron. And you can do the same thing for gravity. So this is a gravitational dress. So the version of this Wilson line operator that I talked about, if you translate that in the language of gravity, is this operation of shining light towards the operator and measure the angle to it, etc. So anyway, so that way you can actually specify the local operation or local excitation inside of ADS. So then it's interesting to understand how to describe this local excitation in the language of operator on the boundary. And this has been worked out. And so here's an answer. So the answer goes as follows. So suppose you have this weakly coupled gravity in untheta space. So you have some kind of local excitation of almost free field. And you want to understand how to describe it in the language of boundary CFT. So you have some field phi, weakly coupled phi in ADS. So then suppose there is a corresponding operator, primary field, in CFT. So then suppose you are interested in describing some local excitation in phi. So how does the local excitation of phi at the position z and x. And you can actually construct the corresponding operator in CFT that creates this excitation. And that operator is defined in terms of CFT operator as actually the linear superposition of this primary operator. Okay? So you can actually create local excitation of phi as a linear superposition of this operator. Okay, and this operator, there is a kernel to it. So this is some kind of Green's function. So this smearing function so you smear this primary field corresponding to this field phi on the boundary, and this smearing function is very well defined, and it has a property that there is actually well-defined expression for it. It's a little bit long formula, so if you are interested in, you can refer to this paper, for example. Okay, around 2006, they have written in this way. And then one of the interesting feature or important feature of this is that g of z x prime goes to d of delta times delta of x prime as z goes to 0. So therefore, this means that phi hat of z of x goes like z of delta of O of x and this is as desired. So you can think of this operator phi half as a solution to wave equation with this boundary condition. Okay. In fact, the choice of such smearing function is not unique, and you can actually choose this smearing function. There is some kind of choice of the smearing function. The reason for this is that if you have one solution to this kind of program, then you can add a linear combination of solution to free wave, normalizable wave equation to find another solution. So it was shown by this paper by Hamilton, Hubbard, and Lifshitz that you can actually make some nice solution to a nice choice of G, which has the following feature. So it is actually the following construction. So it was shown by this paper by Hamilton, Hubbard, and Lifshitz, that the following thing is true. So let me first tell you a little bit about causal structure. So suppose you have, so this is meant to be the boundary on untheta space, and inside of this cylinder is a boundary. So the corresponding conformal field is living on the boundary. So this is SD minus 1, and this is time. So here I'm using the Lorentz signature spacetime so that causality is manifest. So the causality means that if you specify a state of conformal field theory on some particular choice of SD minus 1, the D minus 1 dimensional Cauchy surface, then you uniquely specify a Hilbert space. So in principle, everything about the operator can be known by knowing state on the circle, on the sphere. But they actually, this HKL shows a more refined version of the statement as follows. So suppose you have this sphere, but suppose you don't specify everything. But suppose you only know some subset. Okay, and so let's call this subset as A. Okay, and so first of all, let's look at this boundary region. So suppose you have this boundary region. So this is, suppose I expand this D minus 1 dimensional sphere in this direction, and suppose I specify this A. Okay, so we don't have general relativity student today, but there is a notion of a domain of dependence. Which is the following notion. So in the case of flat Minkowski space, the domain of dependence is just inside of intersection of two light points. And but the idea of domain of dependence is that if you specify a point here, if you go toward the past in any time-like curve, you inevitably pass through this region A. And also if you are in the past of this domain A, if you go to the future in any time-like curve, you inevitably hit this point. Okay, so the collection of all these points are called domain of dependence. So then on the boundary you can draw such domain of dependence. So you can draw such domain of dependence on the boundary. So this is the D of A. Okay, and on the other hand, in the bulk side, you can also ask what is the region which is causally connected to this region, to this A. So then you can have a bulk region, which is again specified by some kind of wedge. So my drawing skill is rather limited, but what I'm trying to draw is this kind of region in the bulk, which is specified by the domain A. And so this is called a causal wedge. Okay? So what these people showed was that if Z and X is in the causal wedge, of A, then phi hat of Z and X can be reconstructed by O of X where X is in the domain of dependence of A. Okay, so this is what these people show. Okay, because of my graphic the skill, limitation of graphic skill, it's kind of difficult to explain this space-time notation. So let me give a limited version of this statement, which I can draw in a simpler way. So suppose I just pay attention to the Cauchy slice. And this is justifiable in the case of ADS because it's globally hyperbolic. So suppose I consider Cauchy surface. So in the ADS side, the Cauchy surface is a boundary. So this is a Cauchy surface. Of CFT. And then there is a disk. This is a Cauchy surface. Of ADS D plus 1. So this is a D plus 1 dimensional disk, a D dimensional disk. Okay, okay. So there is a Cauchy surface for CFT, and there is a Cauchy surface in D. So what I'm saying is that suppose I pick some region A. So suppose I pick some region A. Then there is a corresponding region in the bulk where the boundary of of this region is specified by minimum surface. Subtending A, which means that the boundary of A, this minimal surface ending on the boundary of A. So if then you have this bulk region. So what this HKK, the Hamilton, Cabot, and Lifshitz showed is in this limited situation is a statement that if you have local excitation in this shaded region, then that can be reconstructed by acting local operator limited in this region A. On the Hilbert space of CFT. So this is a sort of more sort of refined version of the correspondence. Okay. So ADS CFT correspondence would say that anything that is happening in each side of the ADS is described by in terms of excitation on the boundary, but that has to involve everywhere in the Cauchy surface. But there is a refined version where if it is in this particular region in ADS, then it can be encoded in this particular region in the boundary. Okay? So there is some kind of local reconstruction of the information. But it causes some puzzle. So some puzzle. About this reconstruction. So let me mention two kinds of puzzles. The first puzzle is the following. So suppose I have, again, the same Cauchy surface. And suppose I have this region A. Suppose I have this region A, and then corresponding the bulk region that we reconstruct. But suppose I have another region B that intersects with it. So then there is actually an overlapping region in A, over here, because this boundary region overlaps. So that means that suppose you have some kind of local excitation phi hat. Phi hat has two descriptions in terms of local operators, smearing of local operators. In A, and then in terms of local operators in B. So that means that this reconstruction map does not seem to be unique. What does it mean that reconstruction is not unique? Is there gauge symmetry? Because we thought that when we have local excitation phi hat in the bulk, there is a physical operator that changes a meaningful physical change to the Hilbert space. But now we are seeing that the corresponding operator in CFT is not uniquely reconstructed. There are actually two, or even in general, multiple of way of reconstructing the same local excitation. So is the notion of local excitation in ADS unique or ambiguous? If it is ambiguous, is there like gauge symmetry, or what kind of thing is it happening? So that's one puzzle. There is another puzzle which is also, which is in some sense more profound, which is the following. So suppose I divide the boundary of ADS into three regions. So this region, and this region. So this is A, this is B, and this is C. Okay? And in such a way that it covers all the boundaries. Okay? But the, 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 reconstruction map would say that if you have any local excitation in this region, it can be reconstructed by A. If there is any local excitation, it can be reconstructed by B. If there is any local excitation, it can be reconstructed by C. What if you have local excitation here? How is this local excitation be reconstructed with region operator in the region A, B, C? Now there is a serious puzzle here because the local excitation at this cannot be reconstructed by operator A alone or operators in B alone or operators in C alone. Right? Because if you just consider local operator in A alone, it cannot be reconstructed from this. But there is actually a very funny thing, which is that suppose you consider, however, the local excitation, at X, at this point, let's call this as X, can be reconstructed by local operator in A union B. A union B. Because if you consider A union B, it's this boundary. And the minimal surface subtending this boundary is this. So that means that this Hamilton Hubbard-Lipschitz reconstruction would say that we should be able to reconstruct everything in this shaded region, including this point. Okay, so this seems to be contradiction. Because on one hand, we are saying that we cannot construct this operator from local operator in A alone and local operator in B alone. But if you consider combination of local operator in A and B, then we can reconstruct the operator over here. This sounds like oxymoron, because isn't it the case that the local operator in A union B is the sum of local operator in A and B? Okay, so this was a puzzle. And this was solved 10 years afterwards. And so I'd like to tell you about it. And this is actually, the solution turned out to be rather profound and makes use of, and the understanding of the solution actually deepened our understanding of how ADA-CFT correspondence works. But before going into that, it's probably useful to tell you a little bit about the notion of entropy of information. So I have 10 more minutes, so let me briefly tell you about, review you about the notion of entropy and information. And because that probably will be a good preparation for what I would like to tell you about the resolution of this puzzle in the next lecture. Okay, so I would like to tell you a little bit about entropy. So in StatNet, that you might have seen in undergraduate, that entropy is given by log of omega, where omega is a number of microstates. So this is how you learn in StatMech. Now in information theory, we learn that entropy is given by minus log of P, where P is a probability of an event A. So if we have a probability of event A happening, then the entropy is given by P. And if, of course, if each microstate is equally probable, then the amount of information is gained by identifying microstate is given by, P is given by 1 over omega, so therefore these two notions coincide. And in information theory, this is a useful measure of the amount of information gained, because, for example, if two events are statistically independent, then the probability of both happening is a product. So therefore, the entropy of both things happening is the sum of entropy. So if two things happen simultaneously, and if these two things is independent, the information you gain by knowing that these two things happen is the sum of these two. So information is additive. So this is the notion of entropy that Shannon introduced. More refinedly, if n events happen, with the probability P1, Pn, in such a way that the sum of all these events is equal to 1, the entropy for such a probability is given by this. So this is Shannon entropy. This Shannon entropy is a very useful concept because it satisfies various desirable properties. So you can easily check that S is not negative and is equal to 0 if and only if some Pi is equal to 0. And another thing is that if the F is maximum, if all Pi's are evenly distributed. Okay. Now this was the case when these probability are independent. For example, A and B are independent in the above, but very often there are correlations, and so in that case, it's useful to introduce a notion of conditional entropy and mutual information. Okay? So suppose, for example, you have two sets of events. So suppose you have two sets of events, A and B. And suppose you can calculate a joint probability. So P of AI, Bj. So obviously, the probability of AI to happen is the sum of P, AI, Bj, summed over all j, because the joint probability is given by P of AB. So if you sum over all the possibility of B, then it gives you P. And similarly, the probability of happening Bj is given by sum over all j of P of Aj B. So this should be obvious. Now, the conditional probability is the following things. So this is, of course, well-known thing, but let me write it out. So this is the probability of Bj happening when you know that Ai has happened. And conversely, okay, so then this leads to the notion of conditional entropy. So conditional entropy is about uncertainty of B when you know that AI has happened. So for example, S of AI of Bj is equal to minus summation of J of P of AI Bj log of P AI Bj. So Shannon entropy tells you about the uncertainty of the information about the certain things to happen. So this conditional entropy is conditioned by knowing that AI has happened and about the uncertainty of B. Okay? And then given this, for example, if we don't know what AI to happen, we may even consider the following quantity: summation I P I A I P P of AI, and then conditional entropy. Okay, so you can also consider this kind of concept, where you average over all these information by probability of AI to happen. Okay, so this is the conditional entropy. Finally, there is a concept of mutual information, which is also an important concept. So this is related to the question of how much is uncertainty of B reduced by knowing A. So how these two events share the information. So that is the difference between uncertainty of B minus the uncertainty of B knowing that A happened. Okay, so in fact you can show that this is equal to SA plus SB minus S of A B. Okay, so nice thing about mutual information is that it's symmetric. Namely that the uncertainty of B is reduced by knowing A by the same amount as uncertainty of A reduced by knowing B happens. Okay, so these are all very useful concepts. Now, I'm running out of time, so I just wanted to give you one example to test whether you have understood this concept. Okay, so here is a question. So you wake up in the morning and you want to go to the school, okay, to take my course, for example. But in order to go out, you need to find a key to your apartment. Okay, and so where is the key? Okay. So you need to guess where your key is, right? So there's a key question. So it turns out that from your past experience, you know that there is a half probability that it is in your pocket. And then there is yet another half probability that it is in one of 16 drawers. That you don't know which one it is. And let's assume that these are in 16 drawers with the same probability. So you have 16 drawers in your apartment, and the key is in one of these 16 drawers. You don't know which one. Okay, so you can ask, well, what is the uncertainty of the key location? Okay, so that's easy to calculate, right? Because S of key location from this calculation, from Shannon entropy is log. Let's choose log of base half to simplify the calculation. So then there are 16 possibilities of each probability is 1 over 32 because there are 16 locations with half probability. So this is 3. So therefore, you try to go out from your apartment, you don't know where your key is. Your uncertainty about the location of the key is 3. Okay. Now you check your pocket, and you find the key is not there. Instead, you have a handkerchief. Now, does that information reduces your uncertainty? Okay, so that's the question. Okay, so let's calculate this conditional probability. So I now know that it was not in the pocket. And then what is the uncertainty of key location? Okay, so you can do the calculation. Now I know that it's not in your pocket, so it's one of these 16 drawers. So from this formula, you can actually calculate this to be 4. So it's greater than 3. Why? Uncertainty is increased by knowing that the key location key is not in your pocket. It's supposed to be an information. It should be an information that you should have gained the information by knowing that key is not in your pocket. But your uncertainty has increased. So why? So that's the question. Okay. So with that, let me end today.